Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We are discussing the Galois correspondence. We've defined the correspondence and set down some of its basic properties. The summary is Theorem 515 we talked about at the end of the last lecture. For a Galois correspondence, the Galois maps are order reversing. If we restrict the codomains to the families of closed elements, then the maps are surjective. The round-trip maps, the composition of the two Galois maps in either order, are closure operators. And the families of closed elements on either side are intersection structures, and so are complete lattices under set inclusion. Moreover, the restricted Galois maps, where we restrict both the domain and the codomain to the closed elements, are inverse lattice anti-isomorphisms. They're inverses of each other, and they are lattice anti-isomorphisms. Another feature of the Galois correspondence is that it is indexed. On both sides of the correspondence, we have an index. The index on the field side, EF, is the degree of the extension, the dimension of E as a vector space over F. And on the group side, we have the group index. And there is a relationship between the indices and the Galois maps. For our purposes, we are going to say that a degree or a group index is either finite or simply infinite. We are not going to distinguish between the different infinite cardinal numbers. So we lump all the infinite cardinal sizes into one category called infinite. Also, for convenience, I'm going to use the term degree for the group index as well as the field degree, so that I don't have to keep saying something about the field degree and then the same thing basically about the group index. I can just simply say the degree, and it covers both cases. You'll see what I mean when we get to it. And as before, with regard to writing the field degree, it is with the tacit assumption that in this case, K is a subfield of L. And we'll do the same thing for the group index. Okay. I must be a subgroup of J. And we use the less than or equal to sign for both subfield and subgroup, so you have to pay attention to the context. Now degree, and so that applies to both field degree and group index, has the following properties. Degree is multiplicative. We have seen way back in chapter 1 that the degree is multiplicative for field extensions, and in the group theory course we proved that group index is also multiplicative. Galois maps do not increase degree. For the Galois group map, that means that if we have a Galois correspondence for a finite extension, Fe, and if we have two intermediate fields positioned thusly, then the degree of the Galois group of K over the Galois group of L is less than or equal to the degree of the field L over the field K. So this is group index, that's why they use parentheses. This is field degree, just square brackets. Okay, so this says that the Galois group map cannot increase the degree. And this is how it would look if we replace the blackboard G. In particular, if L is equal to E and K is equal to F, we just have the single extension FE. The Galois group has size less than or equal to the degree of E over F. This is something we already knew. So I debated whether to put it here or not, and I just left it in. As to proof, so we're trying to prove this inequality here. The value of this group index, to determine this value, suppose we have two elements, two automorphisms in the bigger group. And we look at their cosets with respect to the smaller group. Sigma GLE is equal to tau GLE if and only if tau inverse sigma belongs to GLE, if and only if tau inverse sigma, which is an automorphism of E, so to be in here is equivalent to saying that tau inverse sigma fixes all the elements of L. And we can write that as sigma L equals tau L for all L in capital L. Or in other words, sigma restricted to L is equal to tau restricted to L. So these two cosets are equal if and only if the restriction of their representatives to L are the same. So the two cosets are distinct if and only if the restrictions of sigma and tau to L are distinct. So the index, which is equal to the number of distinct cosets of GLE in GKE, is equal to the number of distinct restrictions of the members of GKE to L. We restrict to L. Each of these restrictions is an embedding of L into E over K. It belongs to this Hom set. And so the index is less than or equal to the cardinality of this set. And I've replaced E by E bar here, so this could be potentially bigger set. So we have this inequality. This is the separable degree, which we know is less than or equal to the degree for a finite extension. And that is the inequality that we wish to establish. As for the fixed field map, we have to do a little bit more work to show that it does not increase degree. So what we need to show is that if J is the subgroup of H, which is a subgroup of the Galois group, GFE, then the degree of fixed J over fixed H is less than or equal to the index of J in H. Well, we know that fixed J is a vector space over fixed H. And the dimension of that vector space is the degree, fixed J, fixed H. We can also produce a vector space of dimension equal to the index, Hj, as follows. Let E superscript H mod J. So this is these are the cosets of J and H. This is the field E. This notation is quite common. If we have two sets x and y, this is the notation for the set of functions from y to x. So this is the set of all functions from the quotient set h mod j, in other words, the set of all cosets of j in h to the field E. This is a vector space, and I'll let you prove that. Its dimension is the size of h mod j, which is by definition the index of j in h. So we have, let's go back to what it is we're trying to show. We have two vector spaces. One has this dimension, the other has this dimension. So to prove that the inequality holds is equivalent to showing that the dimension of this vector space is less than or equal to the dimension of this vector space. Now, there's a simple connection between these two vector spaces. Namely, if alpha is a vector in fixed j, then we can define the evaluation at alpha function, which will belong to this vector space. We'll call it alpha bar, so it's a function from h mod j to E. Alpha bar applied to a coset, h capital J, is h of alpha. Remember that h is an automorphism of E, and alpha is a member of E. First, we have to show that this is well defined, that alpha bar is well defined, because we're defining it in terms of cosets. But if hj is equal to h prime j, then h prime is equal to h little j for some little j in capital J. But alpha fixes capital J element-wise. And so h prime of alpha is hj of alpha, which is just h of alpha. And so alpha bar is the same on h prime j as it is on hj. And that makes alpha bar well defined. Now we can define a map, tau, from fixed j, from this vector space to this vector space. Tau of alpha is alpha bar, evaluation at alpha. Since if we have two vectors in fixed j and two scalars in fixed h, then for every little h in capital H, A alpha plus B beta bar, so this is tau of A alpha plus B beta, applied to a coset is evaluation at A alpha plus B beta, but H is an automorphism of the field E, so it preserves both multiplication and addition. It slips inside, but A and B belong to fix H, and so they are fixed by little h, and so we get this, which can be written this way, showing that tau of A alpha plus B beta is A tau alpha plus B tau beta. In other words, tau is a linear transformation between these two vector spaces. Also, as to the kernel of tau, if tau of alpha, which is alpha bar, is 0, then evaluation at alpha is 0, so h alpha is 0 for all little h in capital H. One of these elements is the identity on E. It belongs to H. H is a subgroup of the Galois group of all automorphisms of E that fix F. So the identity is included there. and that means alpha is 0. So the kernel of tau is trivial, and tau is injective. So fixed J is isomorphic to a subspace of this vector space, and therefore its dimension is less than or equal to the dimension of this one. So we now know that the Galois maps do not increase degree. The restricted Galois maps actually preserve degree. So these are the restricted maps where both the domain and codomain are restricted to closed elements, and these preserve degree. On the field side, if we have closed intermediate fields, H and K, then the degree KH is bigger than or equal to this index because G does not increase degree. Applying F, we get another inequality. But now we have the closure of K and the closure of H. But H and K are closed, so that is equal to the degree KH. We have the same thing on both ends, so we have equality throughout, and so G actually preserves degree on closed elements. And an analogous argument will work for the fixed field map. So we can summarize our results on degree. Galois correspondence for a finite extension, intermediate fields, intermediate subgroups of the Galois group. Degree is multiplicative. That's old news. F and G are degree, non-increasing. This is old news too, but I don't know, I put it in here anyway. And for closed elements, G and F are in fact degree preserving. Because these properties hold, it is said that the Galois correspondence is indexed. Now we can state the fundamental theorem of Galois theory, which I have split into 3 parts. So this is part 1 concerning the correspondence. This is the picture, the correspondence, the Galois correspondence we have here. The codomain restricted maps are degree, non-increasing, surjective, and order reversing. The restricted Galois maps are degree-preserving inverse lattice isomorphisms. So this brief sentence is quite a mouthful. It says quite a lot. Degree-preserving anti-isomorphisms, inverses of each other. That's what I'm calling the first part of the fundamental theorem of Galois theory. The second part concerns which elements of the Galois correspondence are closed, who's closed. And the third part concerns normality. Remember that lower step in a 2-tower whose full extension is normal. The lower step may or may not be normal, and that is something we need to discuss further. Let's now take a look at what I'm referring to as part 2 of the fundamental theorem of Galois theory, who's closed. The first part of the fundamental theorem would be somewhat lacking if we couldn't get a handle on which elements of the Galois correspondence are closed. So that's what we want to look at now. First, let's examine the extreme elements of the Galois correspondence. So we have a field extension Fe. The top elements are E on the field side and the full Galois group GFE on the group side. They must be closed because their closure cannot be strictly larger. There's no room. So that's a simple matter. As for the bottom element, on the group side, it's the trivial subgroup, and the fixed field of the trivial subgroup, so this is the subgroup containing only the identity automorphism, that fixes everything. Taking the Galois group, we get the closure of the trivial subgroup is the Galois group of E over E, and that, of course, is trivial. So the bottom element on the group side is closed. But the bottom element on the field side, which is, of course, the base field F, need not be closed. It can happen that the closure of F, which is the fixed field of the Galois group of E over F, is strictly bigger than F, or in words, there may be some field elements in E, but not in the base field, that are fixed by all of the automorphisms of E that fix F. Just because they fix F doesn't mean it can't fix more than F. As a matter of fact, we're going to prove very soon that the base field F is closed if and only if the extension Fe is Galois. So, in summary, the top elements are closed, the bottom element on the group side is closed, but the bottom element on the field side need not be closed. Another thing we can determine fairly easily is the following. Finite extensions of closed elements are closed. And we can do this with a simple degree argument. So if we look on the field side, and we have this tower FKLE, suppose that K is closed and this extension KL is finite. Then the degree LK is bigger than or equal to the degree of the closures, because the Galois maps do not increase degree. K is assumed closed, so that becomes this. And we can split this by multiplicativity, closure of L over L, LK, but we have LK on both sides, so the degree of the closure of L over L is 1, meaning L is equal to its closure, and so is closed. And a similar argument can be used on the group side, which I'll leave you to do. So, top elements are closed, bottom element on the group side is closed. Any finite extension of a closed element on either side is closed. That's about the most we can say on the group side. But as it turns out, that's enough, because our main interest will be in splitting field extensions for polynomials. Those are finite Galois extensions. And the fact that they're finite means the Galois group is finite. And since the bottom element, the trivial subgroup, is closed, any finite extension is closed, which means all the subgroups are closed. So the group side is, you might say, completely closed. Everything is closed. On the field side, there is more to say. So suppose that FKE is a tower of fields and K is closed, and let alpha be an element of E. Well, we know that any sigma in GKE sends alpha to a root of the minimal polynomial of alpha that lies in E. as we've seen so a long time ago, that sigma is actually a permutation of the set of roots of this polynomial that lie in E. To see when two automorphisms, sigma and tau, in this Galois group map alpha to different roots, but this will give us a handle on how many different roots there might be, notice that sigma alpha equals tau alpha if and only if tau inverse sigma fixes alpha, or in other words, if and only if tau inverse sigma belongs to this Galois group. It's the automorphisms of E that fix K with alpha adjoined. Since these automorphisms fix K, they will fix alpha if and only if they fix K with alpha adjoined. And that's equivalent to saying that the cosets of this Galois group with representatives sigma and tau are equal cosets, same coset. So if sigma alpha is different from tau alpha, two distinct roots of the minimal polynomial, if and only if the cosets are distinct. This tells us that there are at least this many, this is the index of this subgroup in the group GKE, there are at least this many distinct roots of the minimal polynomial in E. So we'd like to get a better handle on this index. Well, K is assumed to be closed. This is the first time we are using that. This extension is finite, and therefore K with alpha adjoined is also closed, and so this index is equal to this degree. If you look at it from the other direction, the Galois group map preserves index on closed elements. This is equal to the degree of the minimal polynomial of alpha over K. So there are this many, this degree, distinct roots of the minimal polynomial in E. Well, that's a full set. This has, say, degree D. There are D distinct roots. We've got all the roots, and they're all distinct. That means that the minimal polynomial is separable and splits over E. Well, alpha was an arbitrary element of E, so it follows that this extension is separable and is a splitting field extension, so it is Galois extension. So in summary, if K is a closed intermediate field, then the extension KE is Galois. This is the upper extension in the tower. Here's the tower. If K is closed, then KE is Galois. Okay. Well, what about the converse? Suppose that KE is Galois. I'd like to show that K is closed. Well, suppose alpha is in the closure of K, so that's the fixed field of the Galois group of E over K. In other words, alpha is fixed by every member of GKE. Now, the minimal polynomial of alpha over K splits over E because KE is Galois, because it's normal. And so for any root beta of the minimal polynomial, there's an automorphism in sigma in GKE that sends alpha to beta. Well, alpha is fixed by sigma, And so alpha is sent to alpha, and therefore beta equals alpha. In other words, the minimal polynomial has only one root, alpha, in E. And so over E, the minimal polynomial looks like this. But alpha is also separable over K, so its minimal polynomial has no multiple roots, therefore D is equal to 1. This is what the minimal polynomial looks like. Its coefficients are in K, so alpha is in K. So alpha was chosen from the closure of K. We find that it must be in K, which means K is closed. So we have shown that K is in fact closed if and only if this upper step KE is Galois. And we have all the details we need for the second part of the fundamental theorem of Galois theory, who's closed. We have Galois correspondence for an algebraic extension. As to the closed subgroups of the Galois group, on the group side, of course the whole group is, the Galois group is closed. The trivial subgroup is closed, and any finite extension of a closed subgroup is closed. So that has two implications. First of all, any finite subgroup of GFE is closed. So if the extension FE is finite, so is the Galois group, and therefore all subgroups of GFE are closed. On the group side, you might say it's completely closed. Every subgroup is closed. For intermediate fields, an intermediate field K is closed if and only if the extension KE is Galois. What does that tell us? Any extension of a closed intermediate field is closed because, I'll write this down here, if K is closed, that means this is, E, is Galois, and so if we have anything in between, this is also Galois. So any extension of a closed intermediate field is closed. Also, if FE is Galois, that means that all intermediate fields are closed, because then F is closed and any extension is therefore closed. So in the case that's most important to us, finite Galois extension, all elements on both sides of the correspondence are closed. So in fact, what I have been calling the restricted Galois maps are just the Galois maps. So they are degree preserving, inverse lattice anti-isomorphisms. And so what that means is that for any tower of intermediate fields and any tower of subgroups, we have this expresses the fact that the two maps are inverses of each other. We start with K. We take its Galois, we take the Galois group of E with respect to K, then we take the fixed field, we get K back. We start with H, we take the fixed field, then the Galois group of E with respect to that fixed field, we get H back. This is an expression of the fact that the two maps are inverses of one another and are in fact invertible. And this is an expression of the fact that they're degree preserving. So I just spelled all this out just so you could see it. Okay. Well, the next step will be part 3, the final part of the fundamental theorem of Galois theory concerning normality.